Good morning, everyone. I am Dr. Bodavula Aslesha from the Department of Aeronautical Engineering. In the class of high-speed aerodynamics, we are going to discuss about energy equation in today's session. So, what is energy equation? So, the basic physical principle of the energy equation is that energy can be neither created nor destroyed. So, it can only change in the form. So, the fundamental principle is obtained from the first law of thermodynamics. Okay, so what we will be doing, we are going to apply first law of the thermodynamics to the fluid flowing through the fixed control volume. So we will be considering a fixed control volume inside that one. So when the fluid is moving through it, so for this particular one, we are going to apply the first law of thermodynamics. So what is the first law of thermodynamics? Where the rate of heat added to the fluid inside the control volume from the surroundings plus rate of work done on the fluid inside the control volume equal to the rate of change of energy of the fluid as it flows through control volume. So once again, so what it is nothing but total energy. So that is rate of change of the energy of the fluid as it flows through the control volume is equal to the rate of heat added to the fluid inside the control volume from the surroundings. So inside the control volume from the surroundings, how the rate of heat is added plus rate of work done on the fluid inside the control volume. So rate of work done on the fluid inside the control volume, how it will be done. So that is the first law of thermodynamics. So we are going to discuss about how this particular B1, that is nothing but we are considering it as a rate of heat added to the fluid inside the control volume from the surroundings, and how the rate of work done on the fluid inside the control volume, how it is done. So these two are equal to the rate of change of energy inside of the fluid as it flows through the control volumes, how the energy has been changed through the as the flow goes through the control volume. So these three terms, that is rate of heat added to the fluid, rate of work done on the fluid, and the rate of change of energy of the fluid as it flows through the control volume. So these three terms we are going to see. So now let us discuss about the rate of heat is transferred to or from the fluid. So what we can do is like this, we can visualize as a volumetric heating of the fluid inside the control volume due to absorption of the radiation originating outside the system or the local emission of the radiation by the fluid itself if the temperature inside the control volume is high enough. So two ways we can visualize. So volumetric heating of the fluid inside the control volume due to absorption of radiation or else local emission of radiation by the fluid itself. So if you are taking as the flow over viscous, then the heat could be heat transferred across the boundary by thermal conduction and diffusion. However, the effects are not considering here. So we are only seeing about the inviscid flows only. So we are not considering these two effects inside the equation, right? So finally, if the flow were chemically reacting, so it might be tempting to consider energy released or absorbed by such reaction as volumetric heating term. So this can be done, this treatment can be done many reacting fluids. So the energy exchange due to chemical reaction is more fundamentally treated as a part of overall internal energy of the gas mixture and not in a separate heating term in the energy equation. So what we are doing, we are telling here that we are not considering the viscous effect. Okay. So if the fluid were chemically reacting, so in that one, energy released or absorbed by these such reactions as a volumetric heating term we will be considering. So this will be done many treatments for the of reacting flows. So this particular chemical reaction which is there, we are not going to create any separate heating term in the energy equation. We are considering this chemical reacting term in overall internal energy itself. Okay, so now let us focus on our first term, that is rate of heat added to the control volume by defining the Q dot to be the rate of heat added per unit mass. And the rate of heat added to the control volume is nothing but Q dot equal to rho into dV. So this is nothing but rate of heat added to the control volume. Now if it is, that is for what? It added to the control volume is for the small elemental volume. If you are considering a control volume, inside that one small element, if you are taking means that one. So if you want to see overall control volume, what it will be there? So it will be like volume integral of Q dot rho dV. So this is the for overall term that rate of heat is added, right? So now we are going for the next term. So next term is what? Rate of work done on the fluid inside the control volume. So now we will be considering a simple case of solid object in motion with a force F is being exerted on the object as sketched in this figure. So we are taking in one object. So it's for that particular object, there is force F is exerted on that one. So the position of the object is measured from the fixed origin by the radius vector r. So from the fixed origin, the position of this particular object is measured. So in moving from position r1 to r2 over an interval of time delta t, the object will be displaced through dr. So this is at time t. So this is a force exerted on this particular one. So at time t, the distance between from the origin to the object is that radius vector is r1. So after seeing if it is moving from r1 to r2, it is like later time, that is as t plus delta t. So what it will be there? So the object is getting moved by dr from t plus delta t. So by definition, what we know? Work done on the object in time t is F into dr. So hence the time rate of work done is simply, we will be taking it as time rate of work done is nothing but this is work done on the object in time delta t is FDR. So the time rate of work done is simply what we can write F into dr by dt. We can write the time rate of doing work. So now what we can write, this dr by dt, we can write it as velocity of moving of the object, right? So what we can state that, so the rate of doing work on a moving body is nothing but F into V. So that is nothing but what we can tell, it is nothing but the product of velocity and the component of a force in the direction of the velocity, right? So this is nothing but rate of doing work on a moving body. So now what we are considering, we will be considering a small elemental in a control volume. We will be taking a small elemental control surface ds. So the pressure on the force on the elemental area is nothing but what? Force minus p into ds. So the rate of work done on the fluid passes through ds with velocity. Rate of work done on the fluid passing through the ds with a velocity v is nothing but what? So p into minus p into ds into v. So that is nothing but rate of work done on the fluid passing through the ds with velocity v. So if you are taking the overall control surface, if you are taking it, so since what we are doing with here, it is happening on the control surface. So that's why we will be having the control surface integral pds into v. Since it is occurring on the body, the negative has come. Sign convention, right? So now what we will be taking? We will be taking the consider the fluid elemental volume inside the control volume. So F is the body force which is per unit mass which is acting on that one. So now the rate of work done on the elemental volume. Previously we have considered the control surface, elemental surface we have considered. Now we are considering the elemental volume due to body force. So the now rho F into dV into V. So this is rate of work done on a control volume due to body force. Now this one is entire summing of the entire control volume. If you are taking this again, what it will be the integral of P F dV into V. Sorry, volume integral of. So this is for rate of work done on the fluid inside volume V due to the body forces. Now what we are having? We are having the fluid inside the control volume on the uncontrolled surface we have, as well as the on the control, inside the control volume also we are having. So the total work done on the fluid inside the control volume is nothing but the summation of rate of work done on the control surface plus the rate of work done due to the body force. So that is surface integral of PVDS. So with negative sign convention, since the pressure is applying on the surface. So integral of volume integral of rho F V into dV. Right? So this is nothing but the rate total work done on the fluid inside the control valve. Now let us consider the third one, that is E3, that is about nothing but the rate of change of energy, right? So to visualize that energy inside the control volume, the system was stationary and the energy inside the system was the internal energy E. So now what we are considering, the system is stationary and the energy inside the system was the internal energy E we are taking. So however, the fluid inside the control volume, if you are taking fluid inside the control volume, which is not stationary, it will be moving along with the flow. So the fluid inside the control volume is not stationary, it is moving at a local velocity v with a consequent kinetic energy per unit mass, that is nothing but V square by 2. Hence the energy per unit mass of a moving fluid is the sum of both internal energy as well as the kinetic energy. So internal energy is nothing but E plus kinetic energy is nothing but V square by 2. So this is the nothing but energy per unit mass of the moving fluid. So E plus V square by 2. So by keeping in that mind that mass flows into the control volume from the left hand side. Now what we are telling, control volume we are considering. So mass is flows into the control volume from left to the left, at the same time the mass is streaming out towards the right. So it is entering towards the from the left and streaming out to the right. So the mass flowing, it brings it certain energy. So when it is going inside, it is coming with certain energy, while at the same time when it is flowing out also, it will be having a certain energy. So the elemental mass flow across ds. So if you are considering a small elemental surface across the ds, so what it is? Rho v ds. So this is the elemental mass flow. So the elemental mass flux of energy across the ds is, so rho v ds into, we have energy E plus V square by 2, right? So by summing over the entire control surface, what it will be there? We are talking about here the control surface again, okay? So rho into surface integral of rho v ds into E plus V square by 2. So this is not entirely total energy inside the control volume, right? So what we have to see? We have to see again, if in case unsteadiness is there, how the rate of change of energy will be there. So if the flow is unsteady, then there will be rate of change of energy due to local transient fluctuations of a flow field variables inside the control volume. So the energy of an elemental volume is rho into E plus V square by 2 into dV. So the energy, hence the energy of the overall control volume if you are taking. So that is volume integral of rho into E plus V square by 2 into d. So now if you are taking about the overall, the time rate of change of, so this is nothing but what? So this is the total energy inside a control volume at any instant time. Now what we need? The time rate of change of energy inside volume due to transient variations of the flow field variables. So time rate of change means dou by dou t. So volume integral of rho into E plus V square by 2 into d. So now if we are considering the overall, what we are having? So that is rate of change of internal energy, right? So dou by dou t of volume integral of rho into E plus V square by 2 into dV So that is due to unsteadiness. Then on the surface integral of the internal energies. So rho VDS into E plus V square by 2. So if we consider the overall equation about the energy equation, that is rate of heat added to the fluid. So rate of heat added to the fluid plus rate of work done on the fluid. So that is equal to rate of change of energy in the fluid as it flows through the control volume. So this is nothing but the energy equation, which means which is also, we will be stating it as energy is conserved. So now what we will be doing, if we are overall combination of all the equation, if you see, then volume integral of Q rho dV, then surface integral of PV ds plus, that is volume integral of rho FV dV equal to heat added and rate of work done, right? That is equal to what we are having. Due to fluctuations, volume integral of rho into A plus V square by 2 dV plus surface integral of rho plus V square by 2 into dx. So this is nothing but the integral formulation of first law of thermodynamics, as it is only applicable for invisible fluid. Now, what the equation which we have seen, it does not include the phenomenon of rate of work done on the fluid inside the control volume by a rotating shaft that crosses the control surface. So, fluid inside by rotating shaft that crosses the control surface, that is W shaft, work done on the shaft, we are not considering. Then rate of work done by viscous stresses on the control surfaces. So work done by the viscous stresses. So W viscous also we have not considered. Then the heat added across the control surface due to thermal conduction and diffusion. Due to thermal conduction and diffusion also we have not included in the equation. In combination with radiation, denote the total rate of heat addition for all these effects is Q. So now what we will be taking? Q dot. So if we are including those above phenomena, that is nothing but rate of work done on the fluid inside the control volume by rotating shaft that crosses the control surface, W shaft, and rate of work done by the viscous stresses on the control surface, that is W viscous. Then heat added across the control surfaces due to thermal diffusion and the thermal conduction and diffusion, then in combination with the radiation. So that we will be writing this Q dot. So due to shaft work done, rate of work done, and the viscous effect we are considering, that is these three included. Then we are having integral of surface integral of rho VDS plus volume integral of rho into F into V into dV. This is due to body force equal to the fluctuation. Due to fluctuation, that is nothing but volume integral of dot by dot T rho E plus V square by 2 into dV on the volume inside the control volume, which is, then we will take on the surface of the elemental surface, how it is acting is total internal energy, rate of change of energy. So integral of surface integral of rho E plus V square by 2 V into ds. So this is when we are including those phenomena as well. So now in this case, if we are applying the divergence theorem, what we know, converting the surface integral to the volume integral, right? So conversion surface integral to volume integral, that is nothing but volume integral of del dot PV ds. So where we are having that surface integral one. So here we have, right, surface integral of rho e v square by 2 into v ds. So now this one, what we can do, we can convert it into del dot this entire term. This entire term is nothing but del dot p we is saying rho into e plus v square by 2 into del. So if we are taking the equation, what we have, so volume integral, if we are taking out, so we will be left out with dou by dou t of rho into e plus v square by 2, and this is also volume integral which we are having del dot rho into e plus v square by 2 into v equal to, so volume integral of qp, right? So that's why we are writing qp only minus del dot pv plus rho f v. So this is after applying the converting the surface integral into the volume integral by using the divergence theorem, right? So now apart from this conservation equation which we have taken, so we will be seeing with the equation of state, that is P equal to rho RT, and thermodynamic relation, that is internal energy is a function of T and V. So the analysis of compressible flow is based on these three fundamental physical principles. So now concluding the all three conservation equations which we have seen. So that is first equation, continuity equation. So continuity equation is nothing but mass can be neither created nor destroyed. So what we got the equation for the continuity equation is that dou by dou t of volume integral of rho dv plus surface integral of rho v ds equal to 0. So conservation of mass is called as a continuity equation, right? So momentum equation is nothing but rate of change of momentum of a body is equal to the net force exerted on it. So from which law we got this particular one is nothing but the Newton's second law, that is F equal to m into dv by dt. So further second law we can write as F equal to m, right? So from this one what we got? We got the equation of dou by dou t volume integral of rho into dv. So again this is further in case of unsteady flow is there, plus rho surface integral of rho v ds into v equal to the volume integral of rho f dv minus surface integral of pds. So this is the conservation of momentum equation. So coming to the last equation which we have seen in today's session, that is nothing but energy equation. So from the physical principle of the energy equation is that energy can be neither created nor destroyed. So it can only change in form. So what we got? So again this particular entire equation is nothing but it is due to unsteadiness, like fluctuation in instant time. So then plus surface, on the surface how the change in internal energy is there. So rho into E plus V square by 2 into V into ds, that is equal to the volume integral of Q dot rho dV minus surface integral of rho V ds plus volume integral of rho F dot V into d. So this is the conservation of energy equation. So this is all these equations which we have referred from the motor and compressible flow with the historical perspective by the J.D. Anderson. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.